Okay. I started telling you a little bit about this new technique that was actually discovered by physicists, but turned out to be very useful to chemists, and that is spectroscopy. And let me just, it relies on a lot of things about light that you already know, but this wasn't actually discovered until 1859. A German physicist named Gustav Kirchhoff and what he found out was that if you took an element in a gaseous state, okay, you heated it up real hot, and so it started emitting light. It started glowing, in effect, and emitting light. Then you could then put that light through a prism, okay, spread out the spectrum. And what you got was not a full spectrum, like Newton saw when he first did his experiments with prisms, but you just saw certain bright lines of light. So let me give you here's the experimental setup. So let's say you got, okay, we have a gas. So here's all the gas atoms in here. And this is my drawing of a flame. So we're heating this up. This is hot gas. And it's emitting light. And let's say we put that light through some thin slit. And on the other side of the slit, we have a prism. Okay, so slit, prism, and then over here we have some screen where we're viewing this light. Now, if this were just ordinary sunlight, okay, if we didn't have this hot gas here that we were getting the light from, but it was just ordinary sunlight, this is just what Newton did, right? And you would get, say, a full spectrum spread out over here from red all the way to blue, right? Blue and violet. Now, but if the light is coming from just a particular gas, let's say that you've got hot sodium atoms in here, vaporized sodium that is emitting this light. What you'll find is you don't get the full spectrum. You just get a few bright slits over here, like you would have just a few lines, rather than, see, here's a full, let me see, well, it's just, say if you have sodium, you would get a bright yellow line. If you had mercury instead of sodium, you would get a really bright green line. And let me actually I have some pictures in one of my books. And I'll pass those around in a minute so you can actually take a look at them. But the principle here is that each element emits light at, how do I word this? At unique characteristic wavelengths. Now, that doesn't mean that there's just one wavelength associated with each element. There's several wavelengths that will be emitted typically by each element. But the wavelengths, that certain pattern of wavelengths will be different for each element. So it's like every single element, in terms of the light it emits, has a fingerprint that you can see on its emission spectrum. So when you see, a bright yellow line exactly at 570 nanometers, you know that's evidence of sodium. And every element is like that. It may have several lines that it emits. A green one, for instance, I mentioned mercury. Mercury has a bright green line. It also has two bright yellow lines. No, sodium, the main line in the sodium is yellow. Mercury, one of the brightest lines is green, but it also has two yellow lines. Yeah, Troy.
You said that Mendeleev had told them that they would find gallium using
spectroscopy. Yeah, right.
Spectroscopy.
Yeah.
Did he say what color and like what wavelength you'd see it at? Or?
No, he didn't know, but he knew that it couldn't exist in any abundant quantities, or people would have discovered it already. And so this was the most sensitive method that scientists had at the time for detecting elements. So what Mendeleev was thinking was, well, if you test like pure samples of zinc, say, and you know exactly where the zinc lines are, and then if you test an impure sample and you find, oh, in addition to those zinc lines, it has a couple of other lines. And those new lines that you see don't belong to any known element that you know, then you've discovered a new element. And that's exactly how they discovered gallium. Nick?
They don't do that today,
Yes, they do this all the time today. Now, not to discover new elements, because basically all the elements have been discovered. But it still has lots of uses. For example, you come across a new object that you haven't seen before but is emitted light. Well, you want to know what it's made out of. You put the light through an apparatus like this, see what lines come up, you know what it's made out of. Okay, Troy.
Could you tell, like, say you have water and you did this test?
Yeah. Spectroscopy. It's a hard one.
Could you tell how much the proportion of oxygen to hydrogen was?
Oh. No. Now that you couldn't, actually the water lines would be different than the lines that you would get from oxygen alone or from hydrogen alone. So they're, compounds, compound molecule will have its own set of lines. Now I should emphasize, actually, fact, let me add to this statement that I wrote on the board. In the gaseous state, in other words, it's not true that if you take any element, any material, and heat it up, that the light it emits will only be at certain very well-defined wavelengths. Yeah, Nick.
If you took like a light bulb and
Yeah.
shone it through a slit
Yeah.
to represent and have the colors, that would be what the little wire was made out of?
Yeah, see, that's what I'm answering right now. And the answer is no. You might think that based on what I've said so far. But that's why I'm emphasizing it has to be a gas. If you take a light bulb, say tungsten filament is in a light bulb, right? And you heat it up really, really hot, which is what you do when you turn on a light. It emits light. Well, it doesn't just emit at the lines that you would see from tungsten. If you actually boiled off tungsten atoms and had them in a vapor state, then they would emit only certain wavelengths, certain lines characteristic of tungsten. If you have them in a solid state, what happens is all those atoms are so close together, they're all interacting with each other. And it's a complicated subject, but basically those interactions between the atoms, they smear out these wavelengths, basically, and so you get light emitted at all wavelengths, so you get a full spectrum. Yeah, Nick.
Oh yeah, but wouldn't that take immense heat to get it so hot that it?
Glowed?
Yeah.
Yeah, it does take a lot of heat. But these tungsten filaments, you can heat them up to thousands of degrees before they melt. Okay. Well, so this is a great new way of analyzing materials and being able to detect even really small amounts of a material. Like I said, if you had a sample of zinc and you heated it up so much that you vaporized some of it, and then you got it glowing, and you looked at those lines, you spot a few that aren't zinc, and don't match up with any other known element, you've discovered a new element. And that's how they discovered in 1875, they discovered the gallium that I told you about this morning. That's right.
So it would be in a mixture, not a compound, if there was the gallium with the zinc?
Yeah, right. But you can detect, small traces of it by this method. Okay, now another, actually I should give you an example of, as soon as Kirchhoff realized that elements, when they're gases anyway, only emit these characteristic lines, he immediately went out and discovered two new elements that people didn't know about before. He's the one that discovered the last two heavy elements of the series that I told you about this morning, the one with sodium and potassium. The last two heavy elements of that series are rubidium and cesium. And the names even come from the spectral lines, because rubidium derives from the Latin for red, and it has a very prominent red line, which is why Kirchhoff named it that. And then cesium derives from the Latin for sky blue, because it has a very strong blue line. Yes, Troy.
So do they also, in the periodic table that they use today, do they also group by what color it is at all, or not?
Oh, no, they don't. This isn't, right, the spectral lines aren't those properties aren't incorporated into the table. They're actually, well, you can see how complex these spectral signatures are when you look at this page of this book I'm going to pass around shows the spectral lines for mercury, calcium, zinc, barium, and you can look, there's a number of lines associated with each element. But you can see how a scientist who is used to looking at these spectrum would, could look at a light spectrum and just name off the elements that were in it. You can pass that around. In fact, my first job when I got out of school, I should tell you, is the military actually hired me to design and test a new kind of spectroscope. And what they were interested in was knowing what the enemy's tanks were made out of. So the idea is, can you figure out what a tank is made out of if you have a sufficiently sensitive spectroscope? And let's say you fire a super high-speed projectile into that tank. Okay, when it hits that armor, there's a burst of light. Okay, if you can get some of that light into your spectroscope and then figure out what lines you see from that light, can you figure out what the other guy's making his tank armor out of? So that's, that is a military application where, and again, the basic problem is there's something out there you'd like to know what it's made out of, but you don't know what it's made out of. Okay, so if you can get it hot enough to vaporize some of it and have that vapor emit light and capture that light, then you can figure out what it's made out of. So that was actually my job for about a year. No. But it's turned out to be an extremely difficult project because, it's one thing under laboratory conditions to, heat up some vapor and get it to glow and put it through a spectroscope. But, the enemy doesn't just roll up in his tank and offer you a piece of his tank that you can heat up and make glow and put through your spectroscope. So you have to stand at some distance away. Now, I actually did tests on a spectroscope that we designed where I went to an Air Force base. They would take a piece of armor, our armor, and fire a high-speed uranium projectile at that armor while I stood behind a protective shield with my spectroscope and looked at the impact and then analyzed the spectrum that I got from that light. So in the end, we ended up concluding that it wasn't a good way to figure out what tanks were made of. But
couldn't you actually, if let's say if you hit like a tank, like the enemy's tank, and they have something fell off of it or something, couldn't you go grab that at night or something and take tests on that?
yeah, if you can get a piece of the tank, that would really help. Now, if you had a piece of the tank, you might not even need the spectroscope. There's probably other ways you could analyze it easier than with a spectroscope. But yeah, no, that's at the time the military hired me, they weren't thinking that clearly. So they had me try to do it this hard way.
That's how you tell what material in a factory is made out of with the spectroscope.
Oh, okay. Yeah. Well, I mean, there's.
Bring it to the lab and then.
Yeah.
So you want
No, it's definitely used in a lot of applications. There's this one application that I worked on was difficult because obviously, you're going to be standing at some distance away. It's hard to collect enough light. Okay. Let's. Now let me tell you one other variation on what I've already told you that turned out to be a very important discovery as well. Scientists figured out that atoms don't just emit light, they also absorb it. And what I just told you about is the emission of the light when you have the atoms in this gaseous state and you heat them up. Well, what Kirchhoff also figured out was that, let's say that you have, instead of that setup that I just drew, we add some elements to it. Let's say you have, well, we have a light bulb that emits light across the whole spectrum. Okay, so it's emitting all the wavelengths. Okay, so it's not a gas. We're heating up a solid here. But now we pass that light through some vapor. Okay, that is an element. Now we pass the light through a slit. Then we have our prism. And our detection screen. Now, what happens in this case? Well, we start out with a full spectrum of light, okay? All the wavelengths. Now let's take, for example, I'll use sodium again. Now, so let's say this is a sodium gas in here. Now, it's not hot enough. It's hot enough to be in a vapor state, but not hot enough to be emitting light. Okay? It's just between the light source and the slit that the light has to go through. Any guesses as to what's going to happen in this case? What are you going to see over here on the screen? Nick?
These like dark lines.
Exactly where the bright lines used to be, right? Yeah, exactly. That's what happens. Because you've got a full spectrum of light coming in, all the wavelengths, but it has to pass through this sodium. Well, it turns out sodium absorbs light at the exact same wavelengths that it emits light. So this cooler sodium here that's not hot enough to emit, when hit with that wavelength of light, it will absorb it. So what you see over here now, instead of seeing a bright yellow line, you see like the rest of the spectrum, and then where that bright yellow line was, you see a dark spot, dark line. No light's getting through because that light is being absorbed by the sodium atoms. And it's the same thing with, so this is, you can call this dark, let me see, dark lines where bright emission, I think there's only one M in emission, lines used to be. And this is due to absorption. Okay, so the, I think so, isn't it? Yes. An element, if it emits lines at a certain wavelength, it will also absorb light of that same wavelength. And so again, this is another way of telling, you know, what this gas is by where it absorbs the light. Now, one of the reasons I wanted to tell you about this was because there's a now I have an interesting story to tell you. I usually just stick to the scientists, but in this case I have to tell you about a philosopher. There was I told you about some of the skepticism about atoms in the 19th century, the fact that there were people out there that thought that scientists shouldn't deal with things like the atomic theory because you couldn't see atoms, that scientists should just deal with what they could see. Well, one of these philosophers who thought this was a French philosopher named Auguste Comte. And when he was writing in the 1830s, he tried to give an example of the kind of thing that scientists shouldn't even think about because it's completely unknowable. Now, if you try to think of, okay, what would be an example of something in the physical world that's unknowable, I mean, completely beyond the reach of scientists, no matter how long they investigate it. Yeah. Well, I mean, think about, we've talked about like the scale of the universe, right? Well, what if you thought of something that was so far away we could never get there? Okay. Yeah. Ben.
Light speed.
Well, probably if Comte had lived in the early 17th century, if he'd lived in Galileo's time, he might have said something like the speed of light. But since that was already known in the 19th century, he wouldn't pick that example anymore. In the 19th century, the example he came up with was as something ridiculous that scientists shouldn't waste their time about because there's no way anyone could possibly know it. Oh, you have a guess, Dan?
Getting to the moon?
No, not getting to the moon. What he named was what stars are made out of. Okay, knowing the material that stars are made out of. Now, to him, that seemed ridiculous, a self-evidently ridiculous thing for scientists to waste their time thinking about, because these stars are, they're light years away. 10,000 times further away from than the sun, at least, and we can never possibly get there. We could never examine them, so on. Yeah.
Did he think it was impossible or just a useless piece of
Oh, no, he named it not as a useless piece of information, but as a piece of information we could never possibly have. So it could never be discovered. Now, because we have to actually stick to, things where we have observational evidence, and we could never possibly go to a distant star and collect material and analyze it in our laboratory and so on. Troy?
But didn't Kant say that you couldn't even trust things from observational evidence anyway?
Yeah, this is a different philosopher, but who was influenced by Kant, the philosopher yeah, similar name. Let me actually spell this for you. Okay, you've got this absorption spectra. So the reason I bring this up, and I think it's a good point. Okay, this guy's name, let me see. And his years are 1798 to 1857. Now, it turns out he died just in time, because if he had lived a few years longer, scientists actually discovered exactly what he cited as his example of something that was completely unknowable. Once Kirchhoff figured out this connection between light spectra and what something was made out of, well, you could look at the light from the stars, from the sun, and start to figure out what the sun and the stars were made out of. Yeah, Nick?
How do you block out all of the light?
Oh, well, you could do that with a narrow field of view telescope. I mean, just direct your spectroscope at the sun and put, a piece of cardboard over it with a little hole. So just let the light from the sun in. Yeah.
What's our sun made of? What's our sun made of?
Arsenic? I'm sorry. Or
Our
what?
sun.
Oh, our sun. Yeah. Yeah, that's what I was going to tell you. The first thing they did was they got light from the sun into a spectroscope, and the first thing they noticed was hydrogen lines. Okay, so they figured out that
Well, wouldn't it just be a full spectrum of colors?
No, yes, it would be, the sun does emit the full spectrum, but if you just look at the outer edge of the sun, so okay, you don't collect light from the whole sun, so here's the sun, and you have a slit leading into your spectroscope that's just collecting light, say, from the edge of the sun there. Well, that material is in a gaseous state, okay? And what you see is a full spectrum, but with certain absorption lines due to whatever materials are in the sun's atmosphere. Okay? And that's how they figured out that, the two major elements that the sun is made out of are hydrogen and helium. I think our sun is actually about 3/4 hydrogen and 1/4 helium or something. Yeah.
Wouldn't that make it like extremely light?
Yeah, if it weren't so big and dense. Right.
There's no gravity.
Oh, it's huge amount of gravity.
Or there's no gravity pulling on the sun.
Oh, from the planets. No, but I mean the sun itself is, 99% of the mass in the solar system is just the sun, and it's pulling on itself. Okay, so like this, this material out here has tremendous gravitational forces on it, just from all the material in the core. Ben.
Would it have any effect on us if we could outstand the heat,
Oh.
the gravitation?
Oh, yeah, no, if we were, let's say, Ben's question is, let's say you have a heat-resistant suit that's really good, tolerant up to 6,000 degrees or so. It's the surface temperature of the sun. And so the 6,000 degree temperature doesn't bother you a bit. But what would just the gravitational force on the surface of the sun do to you? I think it would squash you like a bug. Yeah, it would be really intense. You wouldn't like it. I don't have the exact numbers off the top of my head, but it would.
Like 100 times.
Yeah, I would say something on that order. It would be quite a bit stronger than Earth. So you would feel, you wouldn't want to step on your bathroom scale there. You'd all of a sudden you'd weigh 100,000 pounds instead of, yeah.
Wouldn't you also be like basically squashed if you could somehow like survive on Jupiter, but not really? Wouldn't the gravity squash you there as well?
I don't know. I don't know about. There's two things involved, of course, to figure out the strength of the gravity. You have to know the mass of the body, right? But you also have to know how big it is. The bigger it is, the farther you are from the center, the weaker the gravity. The more mass, of course, the stronger, and you'd have to work out exactly what those factors would be in order to figure it out. I have no trips planned to Jupiter or the Sun, so I haven't worked out the numbers. Okay, but you notice, isn't this you might think that Comte, this philosopher who gave this as his lead example of the unknowable that scientists shouldn't waste their time on, you would think maybe he only picked a pretty good example. Knowing what stars are made out of, billions and billions of, untold billions of miles away. We can never get there. And yet, here are these guys, way before there's any space program, and they figure out what these stars are made out of just by looking at the light. Now, other interesting thing about this, the hydrogen spectrum was the first thing they found. That was in 1862. The helium they identified as another major component of the sun in 1868. Now, helium hadn't even been found on Earth at the time. Nobody knew about helium. But they saw these spectral lines, and they said, well, that's not any element that we know of, but it obviously exists, and so we'll make up a name for it. We'll call it helium. Yeah.
Where did they start to find lots of it?
What?
Where did they start to find lots of helium?
Oh, well, it wasn't found on Earth until the 1890s, and they found it from studying radioactive samples of uranium. I'll tell you about that later, why helium is associated with uranium. But but you can get helium gas basically coming out of certain radioactive materials.
So our balloons are filled with this radioactive gas.
No, the helium itself isn't radioactive. The stuff that shot the helium out is radioactive. So it's the helium doesn't react with anything. I mean, you could breathe it all day long; it wouldn't bother you. Yeah.
Did they name it helium after the sun?
Yeah, right. So this was because it was found on the sun. That's why it was named helium, for helos, with the Greek for sun. And then they found other trace elements of materials by looking at the sun's atmosphere, the absorption spectrum of the sun's atmosphere. They found some carbon, some oxygen, some nitrogen, and even a little bit of sodium. So one of the interesting things that came out of this was, there'd always been speculation about, the sun and the stars are such different objects than the Earth, that maybe they're made out of completely different materials. And yet, no, find out that everything in the universe is made out of the same stuff. Yeah, Drew.
So a question about the sun. The sun doesn't even really have like a surface. You couldn't really walk on it, though, could you?
No, I mean, it's just on the its outer atmosphere, of course, is just a gas, and then it just gets to be a denser and denser gas as you move in until finally, of course, in the core, it's really dense, just due to the gravitational pressure. Oh, yeah. Way before. Okay.
Do you know where they get helium these days? Because it's pretty rare, yet you can buy it at Toys R Us by the bottle really cheap.
Yeah, I mean, well, any alpha emitter produces helium. Now, if that means anything to you, I mean, it's a form of radioactivity. That's why they originally found it in uranium. But I mean, how else you get it? I'm not sure. But
Extract it from the atmosphere.
well, I mean, there's a lot of radioactivity. I mean, and you can. I mean, there is some helium in our atmosphere, not very much. So
Well, it's bad for us. Like if you swallow it.
it's not bad for you.
So you can swallow it.
You can breathe it if you want. I mean, as long as you need some oxygen. I mean, the only thing that would be bad for you would be breathing just helium. That would kill you because it's like breathing nothing. So it'll kill you the same way suffocation will kill you. But it doesn't react with, I mean, chemically, this is what was later called the noble gases, or one of the inert gases, which just means there's a certain group of gases that I haven't told you about yet that don't react with much of anything, and helium's one of those. No, you're thinking of hydrogen. Actually, that's why they stopped making balloons out of hydrogen and started making them out of helium,
Yeah.
because making them out of hydrogen turned out to be rather dangerous.
Isn't that what the Germans did?
Hmm?
Isn't that what the Germans did?
Yeah, right. That's the Hindenburg. That was a hydrogen balloon that didn't do so well. Yeah.
The one that had a big explosion.
Right. Right. Okay. Well, we'll get back to a little more chemistry next time.